Hello students, welcome to the next lecture. In this session we will be discussing boost regulators. So you know that boost regulator, as the name indicates, the output voltage of which will be greater than the input voltage, and as the name indicates, it is a regulator. That means the ripple content in the output will be reduced because of the presence of the filters that is used in the circuit. So it is similar to the buck regulators. The only difference is the output voltage here will be greater than that of the input voltage. So by the end of this session, you will be able to describe the operation of boost regulator. So this is the circuit where a single transistor M1 is shown here in the circuit, which is acting as a switching device. Okay, and you are familiar that the boost converter circuit will be, the arrangement of the circuit and the components will be slightly different from that of the buck converter. So in this regulator, boost regulator, all we need is a DC constant voltage, that is Vs, the input voltage. What we have the inductor L, the filter L, the switching device M, the transistor is acting as the switching device or the chopper. Then we have a diode for regulation and the filter C, capacitor, that is used for reducing the ripple content in the output. And obviously you have this resistive load, which is shown here as low. So all the parameters in the circuit are named here. So Vs is your input voltage. So obviously the Is will be the current due to the input source. The voltage across L, inductor, is represented as EL. You can take it as VL also, no problem. The current flowing through the inductor is represented as IL, and I1 is a current that is flowing in the circuit when the switching device is off or the chopper is off. The current that is flowing through the capacitor is represented as IC, and I0 is your output current across the load. So the output voltage what we measure across the load, it is represented as V0 or VA. VA is again the average output voltage what we are measuring at the load. So the understanding of this boost regulator circuit again can be done in two modes: when the chopper is on and when the chopper is off. So whenever this switching device is on, we know the circuit would look like as shown here in mode 1. When the switching device is turned on, the switch we are shown here as a short circuit. It is shown like this. So in that case, the diode is not conducting, right? So the circuit, the input circuit, you will have like this. You have the input voltage, DC source, inductor, the switch is now turned on. Okay, and across the load will be getting the current due to the capacitor. So that's why this separate circuit is shown here, wherein there will be a current at the load because of the capacitor current that is flowing through. So that is shown here as a separate circuit here. But we are aware that the diode will not be conducting in mode 1. Okay. And when in mode 2, that is when the switching device is turned off. When the switching is turned off, we know that it acts as an open circuit. So that is when the inductor which has stored the energy will be dissipating the energy via the diode, the capacitor and the load. So because of the property of the inductor, the voltage will be reversing here. So this point, the potential at this point will be higher compared to this, where the energy is dissipated from the inductor. So that will make the diode to be forward biased and which will conduct. So that's why in mode 2, you have the inductor, the diode conducting. So the circuit will be completing like this, and you have the capacitor and the load. So the current flowing through will be via the inductor because of the energy stored in the inductor. So that is mode 2. So we are aware that in mode 1, when the chopper is on, or when the switching device is on, the current due to the constant DC supply will be that is the current IS will be flowing through the inductor, wherein the current via the inductor will be slowly linearly raising, right? So when the switching device is turned on, right? So the current via the inductor will be slowly increasing. Okay, that means the inductor is now storing the energy, right? So when the switching device is turned off, that is in mode 2, now the energy that is stored in the inductor will be dissipated. So the IL will be now decreasing. So the energy, the current in the circuit will be via this inductor or because of the inductor. So the current uh, IL will be now decreasing, falling from the higher level to lower level. Okay, so that is that is how the working of mode 1 and mode 2 can be understood. So to be more precise, we will go through these waveforms. You are familiar with this. I hope you are able to relate the explanation here. So the circuit in mode 1 and mode 2 is shown in the right hand side, and the waveforms are shown here. So during when the switching device is turned on, so say during this period, so this is your IL, the inductor current. So it is raising from I1 level to I2 level. Okay, so during this time period. And when the switching device is turned off, that is at say T1, then you see the inductor current IL is dropping, falling from I2 to I1 level. So this we call it as peak to peak ripple inductor current, right? That's we are representing as delta I. Okay, and if you observe I1, as I mentioned earlier, I1 is the current that is dissipated because of the inductor in the circuit, right? So you can see I1 will be when the power switching device is turned off in this time period, the I1 current will be falling from the maximum value I2 to I1. So that is what is shown here. Now, if you observe the capacitor current IC, okay, so capacitor current IC, if you note there, when the switching device is turned off, the capacitor current will be again released or discharged. The current is discharged via the capacitor. So that is why it is shown as dropping. And when the device is turned on, you can see there is no connectivity for this first circuit, I mean initial circuit and the last circuit that is across the load. So in that period, when the power switching device is turned on, so you can relate here. So that is when the energy or the current flowing in the circuit via the across the load will be because of the capacitor. So that's why it is shown as negative. So the capacitor will be discharging current, right? So that's why the negative current is shown here when the power switching device is turned on. All right. So if you observe the voltage across the capacitor, now we will start from here. So when the power switching device is turned off, that is when it is in mode 2, the circuit is in mode 2, then the energy stored from the inductor will be flowing through. So the current, the circuit current is because of the inductor. So the capacitor will be now getting charged. So as you observe here, the voltage across the capacitor is slowly raising, or you can say the capacitor is getting charged from say lower voltage to the higher voltage, which we can call it as delta VC. And when the power switching device is turned on, if you observe in the initial state from 0 to T1, that is when the capacitor will be discharging. So the voltage is dropping from higher value to lower level. So that is about the waveforms of different parameters. And if you observe the output current I naught across the load, it will be almost uh, discontinuous. So the output what we get at the load will be continuous in nature. The ripple factor will be very less because of the filters L and C. So based on the values, obviously to reduce the ripple content, the capacitor value and the inductor value should be quite large so that the ripple will be reduced to maximum extent. So larger filter capacitor and larger inductor will be used in such circuits. So we'll go to the mathematical expression of these uh, circuits. So assuming that the inductor current rises linearly from I1 to I2 in time t1, we can write Vs, which is your input voltage, as L into I2 minus I1 by T. So which can be written as L into delta I by T1. So delta I is nothing but I2 minus I1, which is the ripple inductor current. So you can call it as equation number 1. Or you can write it in terms of T1. So T1 will be equal to delta I times L divided by Vs. Call it as equation number 2. And the inductor current falls linearly from I2 to I1 in time T2, right? We have observed in the waveforms. So that we can write it as Vs minus Va, where Vs is your input voltage and Va is your output voltage, the average output voltage. So which can be written as minus L times delta I by T2. Okay. So you can call it as equation 3, or if you write in T2 terms, so T2 will be equal to delta I times L divided by Va minus Vs. So observe that the negative parameter has gone there because of Va minus Vs. So call it as equation number 4. So where delta I, we know that it is I2 minus I1 is the peak to peak ripple current of inductor. So from equation 1 and equation 3, if we equate for delta I, we will get Vs T1 by L is equal to Va minus Vs into T2 by L. So substituting T1 is equal to K times T, where K is your duty cycle, and T2 is equal to 1 minus K times T, which will yield the average output voltage. So from these two equations, if you substitute T1 is equal to KT and T2 is equal to 1 minus KT, you get average output voltage VA given by Vs into T by T2, which will be equal to Vs by 1 by K. Call it as equation number 4. From the above equation, you will get 1 minus K is equal to Vs by Va. So let us call it as equation number 5. Now substituting K, the duty cycle, is equal to T1 by T. which can be written as T1 into F. Okay, in the above equation we will get T1 is equal to VA minus VS by VAF. Let us call it as equation number 6. Now, assuming that the circuit is a lossless circuit, then we know that the input power will be equal to the output power, which can be written as VSIS is equal to VAIA. So substituting VA here from our previous equation, VA is equal to VS by 1 minus K. Substituting that, you will have, from which you will get IS is equal to, which is your average input current. Average input current IS is equal to IA by 1 minus K. Call it as equation number 7. Now, the switching period T can be found from T is equal to 1 by F, which can be written as T1 plus T2, which is our on time plus off time. Okay, so substituting T1 and T2 from our previous discussions, what we had, T1 is equal to VA minus equation number 2 and 4. Okay, substituting 2 and 4 here, delta IL by VS plus delta IL by VA minus S, you will get delta IL into VA by VS into VA minus S. Just substituting there, simplifying things. So this will give peak to peak ripple current. So delta I, you will get it as VS into VA minus VS by F into L into VA. Call it as equation number 9. So writing the same thing in terms of duty cycle, you can also write it as delta I is equal to VSK by FL. So call it as equation number 10, wherein substituting the above equation in terms of K and 1 minus K. Okay. Now, when the transistor is on, the capacitor supplies the load current for T is equal to T1 time, right? So the average capacitor current during T1, it is given by IC is equal to IA. If you recall the circuit, we will go back to the circuit there. Yeah, we'll go back to circuit wherein IC is equal to IA, right? So the peak to peak ripple voltage of the capacitor, it can be given as delta VC, can be written as VC minus VC for T is equal to 0, right? So which can be taken as the capacitor across voltage VC directly, that is 1 by C within the limit 0 to T1. So we will take the time duration 0 to T1 only, okay, wherein the voltage, it can be written as in terms of the capacitor current IC with respect to dt, right? So you will get 1 by C 0 to T1, integration 0 to T1. So IC, in place of IC we will write IA. So wherein you will get IA into T1 by C. That is your ripple voltage across the capacitor. Call it as equation number 11. Now substituting T1 is equal to VA minus VS by VA into F from equation 6, we get, substituting T1 there in our previous discussion here, substituting T1 there, so you will have delta VC is equal to IA into VA minus VS by VAF by C. Or you can also write it as delta VC is equal to IA K times IA into K divided by FC. Call it as equation number 13. So that will give you the voltage across the capacitor. That is the ripple peak to peak voltage across the capacitor. Now, the conditions for continuous inductor current and capacitor voltage. Okay. So if IL is the average inductor current, the inductor ripple current delta I is given by twice of IL, right? Okay. So using equation 4 and 10, using equation 4 and 10, 4 is here and equation number 10, okay, substituting these two here, we get VSK by F into L, which is nothing but 2 into IL is also equal to 2 into IL is nothing but IA. We will write it as IA, that is in terms of VA, right? So VA is equal to 2 into VS by 1 minus K by R, wherein I hope you are able to relate that equation number 4. So VA is equal to VS by 1 minus K. So in terms of VA, if we write in terms of I and R, so it is IA into R, right? So IA will be equal to VS by 1 minus K into R. So that is what we have written here. So 2 times Vs by 1 minus K by R. So which gives us the critical value of the inductor LC. So from the above equation, if you simplify things where Vs cancels, you will get L, the critical value of the inductor L will be equal to K into 1 minus K R divided by 2F. So this is your inductor value. So which again, if you see, it depends on the duty cycle K, right? So call it as equation number 14. Similarly, the average capacitor voltage. If VC is your average capacitor voltage, the capacitor ripple voltage delta VC, it is nothing but 2 into VA, the output voltage, right? So using equation 13, we get IAK. Where is your equation 13? Yeah. So equation 13, substituting here, IAK by CF is equal to 2 into VA, which is also equal to, writing in terms of IR, IA into R, which will give us critical value for the capacitor as C is equal to K by 2FR, where IA cancels here in the above expression. So C is given by K by 2FR. So call this as equation number 5. So these are the expressions or the mathematical expressions which can be used to analyze and design the boost regulator. So to design the boost regulator, what should be the value for the inductor and the capacitor, we have derived here with the critical value of the inductor and capacitor. And to analyze the expression there, we have understood the different terms there, that is the ripple current of the inductor. Then we have understood how to analyze the peak-to-peak ripple voltage of the capacitor, then the voltage across the capacitor, and based on the inductor current, variation in the inductor current, how the circuit responds. So we have observed the waveforms as well. So that's about the boost regulator. I hope you have gone through the derivations there and you have understood. So this boost regulator uses a single transistor. That's why it has a very high efficiency. And the current is continuous. That is, this type of boost regulator gives us the continuous load current. So go through. If you have any doubt, clarifications, kindly get back.